So yes, the correct answer here is D, SP, D in the middle, and the F blocks. All right, so we're going to start out talking about, we're going to kind of be alternating back and forth between trends and properties that you learned about in honors chemistry and ones that go beyond what you learned in honors chemistry. So we're going to start out with one that you did learn, which is trends in atomic radius. So the atomic radius is actually tricky to measure. Because remember that our electrons don't actually live in those circular orbitals the way that planets go around the sun. They're actually they exist in a cloud of probability of the location of any given electron at any given time. So figuring out where the atom ends is actually a difficult proposition because the boundary is fuzzy. There's not really a line that we can draw around it. One of the ways that we can get around this is by looking at what we call the covalent radius. So for nonmetal elements, we can basically stick two atoms together of the same element and look at the distance between the nuclei, which we can measure pretty easily, and then have that and call that the atomic radius. It's obviously not perfect. There are a lot of other ways that we can look at this or calculate it. So if you go to the best website on the internet, ptable.com, if you recall from Honors Chem, the landing page, the default landing page is the Properties tab. And when you're on the Properties tab, there's this sidebar with all these different things that you can select. So for example, if we hit radius, what we end up with is the bottom, on the table, but not on the big block here. On the table, the bottom number is no longer the atomic mass. It is now the radius in picometers, as it tells you here. And you can see that the radius decreases as we go from left to right across the table, and it increases as we go from top to bottom. Why does it decrease as we go from left to right? Why does the atom get smaller? Why does the radius get smaller? Edward? Very, very close. Winnie? Oh, that's not your hand. Do you remember? Go ahead. The nuclear charge increases, yes. So the number of protons increases. The number of electrons does also increase, but the effect of the charge, the nuclear charge on each of the electrons at an energy level is pretty much equal. So more protons, so the effect of having a greater charge comes from having more protons in the nucleus. So you're on the right track. So the more protons we have, the higher the nuclear charge is. And since, yes, we are also adding electrons, but those electrons are being added to our valence shell, to the same energy level. And so we're not increasing our shielding. So we're increasing our actual nuclear charge and also the effective nuclear charge. So what we end up with is a stronger force of attraction between the nucleus and the valence electrons because we have more protons. That stronger force of attraction pulls them in a little bit tighter, makes it a little bit smaller. Okay. Why does the radius increase as we go down a group? Patrick? Yeah, we're adding more energy levels, and those energy levels have to be on the outside of the previous energy level, so they are farther away. There's also a reduction in the force of attraction there, not just because of the distance, but also because of the shielding of the core electrons as we get further and further out to the higher energy levels. All right, so we are increasing our radius as we go down within a group. We are decreasing our radius as we go across within a period. If you look carefully here, you'll notice that there's a drop-down menu for radius, and there are several options. We can have calculated radius, empirical radius, covalent radius, van der Waals radius. That is because we can't always have two atoms stuck together and measure the distance between their nuclei. Things get more complicated when we get into the metals and also when we get into the noble gases, because remember that helium, neon, and argon never bond with anything. So we can't get a bonding diameter for those because they don't bond. So there are other ways that we can get at an atomic radius. You don't need to know all those different ways. You just need to understand that that's the covalent the distance between the nuclei is one way that we can get at it, and that it can be complicated. Okay. All right. So this is page 7 on your study guide, where it kind of dissects the trends that we were just talking about. So as we go across a period, the atomic radius gets smaller because we are getting a higher nuclear charge, but the electrons are going into the same main energy level. So that's going to pull the electrons closer. The higher effective nuclear charge is going to pull the electrons closer, make the atom smaller. As we go down the group, the number of occupied energy levels increases, and so we're going to have more electrons on the outside of the previous energy levels, but also we're going to have that weaker attraction in general, both from distance and from the shielding. Okay. All right, so you might get a question that asks you to look at, to compare some elements in terms of their atomic radius. You might also get a question that asks you to look at a graph. So a lot of times you might see graphs of, say, atomic radius across period 3. So this is going from sodium to argon, and we're looking at the atomic radius, which is decreasing somewhat as we increase our nuclear charge. And again, that's the electron shielding is remaining constant, and so it's the same graph. It's just these slides are detailing what we already talked about. So we see this decrease in atomic radius across a period. You could also see a graph of atomic radius by going down a group. So this is an example of group 17, fluorine down to astatine, looking at atomic number versus atomic radius, and you can see that the atomic radius goes up as we go down the group. You may also have to look at a graph like this that has all of the elements. This should look familiar. Something like this should look familiar to you from honors chemistry because we made you graph these. At least one of the periodic trends. Everyone had to make a graph that had this sort of sawtooth function, because as we go from one period to the next, we see this jump in the atomic radius because we're adding another energy level. And then across that period, we see a decrease, and we see a jump for the next period, and then a decrease, and so forth. So you want to get familiar with what these graphs might look like and be able to identify, just looking at this graph without having a y-axis labeled, what periodic trend could this be, all right? And I'll give you guys a chance to practice that later. Another way we can do this, and this is what I'm going to ask you to start doing on your blank periodic table, is to start thinking about, okay, as we go across and as we go down, what's happening to each of the different trends. It's a good way to sort of create a study guide for yourself. So just starting with atomic radius, now there's a couple ways you can do it. You can draw the arrows towards the increase, or you can always draw the arrows in the same direction, left to right, top to bottom, and then say if it's an increase or a decrease. Whatever makes the most sense to your brain. I like doing it this way, but I've seen it done the other way as well. So as we add a new trend, each new trend that we add to this picture, you're going to start adding it to your blank periodic table. And it may get messy, and I will probably, upon thinking about it more, I'll probably provide you guys before the quiz on this topic, like a smaller version that has more room on the outside for you to write down all those things. But for now, these are the ones that I already had printed out. So atomic radius, we talked about in honors chemistry, pretty straightforward. Just has to do with the number of protons and the number of energy levels changing. You might also want to write why. You could also write, for example, as we go from left to right, the effective nuclear charge, right, ZF increases. as we go from top to bottom, the Z effective decreases. You could write it in terms of forces of attraction, just to kind of give yourself a sense of why are all these things happening, not just the fact that they are. The goal is to be able to not have to memorize every single trend, to be able to come up with the reason for the trend, and then be able, I mean, if you memorize it, that's great, but there are a lot of them, and so the goal is to be able to think through what way would this trend, this particular property go. Okay. So that's atomic radius. We've done that. But another thing that we're going to now add, and this is page 8 to 9 on your study guide, is the radius of ions. So this is something new that we didn't really cover in honors chemistry. So depending on what type of ion is formed, different things are going to happen to the radius of the atom. Okay? If we are, our metallic elements are going to lose electrons to form positive ions. They're going to lose electrons to get back to the full octet of the previous energy level. So they're basically going to be losing a whole bunch of the valence electrons and going down an energy level, which is going to make them smaller. Okay? Our nonmetals are going to be gaining electrons. Now you would think, well, they're gaining electrons, but those electrons are going into the same energy level, so there shouldn't be any effect. But there is a little bit of an effect in that the electrons are all repelling each other, so a fuller valence level is going to be a little bit bigger. Now, if we're talking about and also the fact that you're going to have more electrons than protons. So the effect of the charge of the protons pulling on the electrons is going to be a little bit less than it would be without extra electrons. Okay. We talked about this idea of isoelectronic species in the last topic. So these elements are all isoelectronic with neon, or these ions. So sodium will lose 1 electron, magnesium will lose 2 electrons, aluminum will lose 3 electrons, fluorine will gain 1 to be like neon, oxygen will gain 2, nitrogen will gain 3. This is actually not super helpful, but I actually do like what's in your study guide. So in your study guide, they talk about the positive ions and the negative ions sort of separately. So you can see that the sodium atom is 160 picometers, radius is 160 picometers. The sodium ion is only 102, because again, we've lost an entire electron shell by losing that 1 electron, okay? So even though that 1 electron is only ever going to be in one place at a time, the probability cloud is significantly bigger when we have that electron in the third energy level than when we lose that electron and only have the 2 energy levels left. Okay, and now these valence electrons, these are now the valence electrons, and they're pulled in pretty tightly because there's 1 less level of shielding around in between them and the nucleus than there was when we had that 1 valence electron in the 3rd energy level. Okay, and you can look at chlorine as the example of a negative ion. And again, you can see the chloride ion is actually bigger. So we've added 1 electron. All we're adding is 1 electron. You're thinking, well, it's going into the same energy level that all the other ones were in. But again, there's going to be this increased repulsion for having more electrons in that outer shell, and a decreased attraction from the nucleus. So negative ions are going to get bigger than the atom. Positive ions are going to be smaller than the atom, the neutral atom. And you will see this if you look at a graph. This is the kind of graph that you might have to recognize or produce on a paper 2 question. So looking at the trend in ionic radius, again, we're just looking at period 3. So we're going across from sodium to argon. And you can see that, like atomic radius, within the positively charged ions, we see a decrease. Okay, because these are all isoelectronic with each other. So these are isoelectronic with neon. Okay. And as we add protons to having the same number of electrons as we're going across, we are still going to see that decrease within those positively charged ions. As soon as we flip over to negatively charged ions, though, now these guys are all going to be isoelectronic with argon. Okay, so we have a whole nother full energy level, or full octet anyway, in the outer shell here. So rather than having two electrons in 2 energy levels, here we have electrons in 3 energy levels. So we see this big jump. And then within those ions, we still see that decrease due to the increased number of protons going from left to right. Okay. So if you were asked to draw this, you would have to show the decrease here, the jump, and then the decrease again, probably in order to get full points. Okay. And then they might show you something like this as a graph to say, what periodic trend is this? The fact that it jumps up in the middle of the period would be your signal that there's something going on here that's changing. We're changing from positive ions to negative ions. Okay. And this is just, I really like this image, but for some people it kind of explodes the brain. So if it's too much, don't worry about it. What I like about this image is that the atomic radius is in gray. So you can see the neutral atom getting smaller as we go across the period. And this is just our S and P block elements. We're not including the transition elements here. But you can see going across from starting on the left side of the S block, going into the P block, going to the end of towards the end of the P block, you can see the gray spheres are getting smaller. And then you can also see, so the cations are pink, and you can see that they're all smaller than the neutral atoms. And then within the pink, they're also getting smaller as we go across. They're getting bigger as we go down, just the same way that the neutral atoms get bigger as we go down, because we're still adding an energy level from row to row. So you can see the trend in both the atomic radius and the ionic radius, and you can see where when we flip, this doesn't include groups 4 and 5, because 4 is complicated because it can kind of go either way. And 5, I don't know, they just didn't put group 5 in here. 5A, sorry. So group 15, 16, and 17 are here. But you can see even with just group 16 and group 17, you see the jump in the size of the ion, which is now bigger than the neutral atom. And also it still follows the trend. It gets smaller from 16 to 17. These sizes are a little, not hugely different. Remember that these and these are all isoelectronic with each other, right? They're all going to be isoelectronic with neon. These and these are going to be isoelectronic with argon. These and these are going to be isoelectronic with krypton, and so forth. So you don't see a huge decrease in the ionic radius in the negative ions, but it's there. It's consistent. And then again, you still see the increase going down the group. So the overall trend is maintained. You just have this jump between cation and anion. Okay. So if I were drawing this, of course I don't have a periodic table on me, but if this was a periodic table and I were drawing my trend, I might say something like ionic radius decreases. And then I might draw like a little jump to up here, showing that the ionic radius decreases, but it goes up, and then it continues to decrease. Or, some way of showing yourself like a broken arrow or something like that, just to represent that there is a break there in the middle. However you want to do that is fine. Okay. Our next trend that we're going to talk about is ionization energy. And it's specifically, when we talk about it in honors chemistry, we mostly just said ionization energy. But we're going to be a little bit more specific now, and we're going to say first ionization energy. It's the same thing. If you come and take year 2, the higher level curriculum includes successive ionization energy. So the second ionization energy, the third, and so forth, and patterns in that. But we're just concerning ourselves with the first ionization energy, which is the same ionization energy we talked about in honors chemistry. It's important to know the actual definition of this. Just like it was important to know the definition of periodicity, it's important to know exactly how ionization energy is defined. Now, they will accept the energy required to remove one electron from one atom, but there's a couple things that would be, there's one thing that you have to include and another thing that it's better to include. You have to include that the atoms are gases, okay? They're gaseous atoms. So that's how the ionization energy is measured or calculated, is in vaporized samples. And that's because if you think about the particles in a gas are separated from each other, so we can talk about each atom sort of individually. When we have a solid or liquid, there's a lot of intermolecular forces that could affect the ionization differently. When we have metals, they actually are already ionized when we have metallic bonds, which we'll talk about in the next topic. So it's important, if you're asked for a definition of ionization energy or asked to, choose the correct definition, that it's a gas. And it's typically, the more technical definition is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. Okay, so that's typically given in something like kilojoules per mole. So that's, it's not just energy required to move 1 electron, it's the energy required to remove 1 electron each from a mole of atoms. Okay. And this is one way that you can indicate it. So X here is just indicating the element symbol. So specifying that it's a gas, that you're going from the neutral atom to a single positively charged, an ion with a +1 charge and 1 electron. This is the case even if we're talking about nonmetals that tend to form negative ions. When we talk about ionization energy, it's still how much energy it takes to remove 1 electron. So oxygen is never going to form a +1 ion without us putting a lot of energy into it, okay? It's not going to do that in nature. However, that is still the definition of ionization energy for oxygen, okay? And yeah, they have it written here as kilojoules, moles to the -1. Remember, that means it's just in the denominator. Moles are in the denominator. And what's going to make ionization energy higher is if there's a bigger Coulombic force of attraction. So if I have this relatively weak magnet that I bought at Target, came from some crappy plastic thing, it's pretty easy for me to take it off of the board. It does stick to the board, but I can take it off pretty easily, and there's only so much that I can use, so many papers that I can put between this and the board before they start falling down. These neodymium magnets, I really have to put some effort into peeling them away from the board. Same kind of idea. If there's a stronger force of attraction between the protons and those outer electrons, which are the ones where the electron's going to get removed from is that valence shell, then it's going to take more energy, more effort to remove that. Okay. So, generally speaking, if we look at this on P-table and we clicked over to ionization here, Again, you can do a drop down and it'll give you first through 30th. So the first amount of energy it takes to remove the first electron, and then the amount of energy it takes to move the second electron, and then the third electron. But we're just going to focus on first. Yeah, so it can go in all directions. And what you can see here is, generally speaking, we are increasing our ionization energy. So our high is blue and low is lightest, brightest green. And you can see that, generally speaking, as we go from left to right, we're increasing our ionization energy. Why is that? Why does our ionization energy increase as we go from left to right within a period? Patrick? Okay, yes. That would not get you a point if that was the question on the test. You're not wrong, and this is the way we talk about it in honors chemistry. Okay, we talk about it very anthropomorphically. Who wants more electrons? Who wants to give up electrons? And I will probably still talk about it that way to you guys. But what is changing as we go across from left to right that's going to make the ionization energy bigger? Yeah, want to try again? Okay, yes, and that is because of what? Stronger force of attraction, because we have what? More protons, higher effective nuclear charge. Okay? As we go across within a period, we have more protons, we have a stronger effective nuclear charge. So we have stronger attractive pull on those electrons. The stronger the pull, the harder it is to pull them off, the higher the ionization energy that we have to put in to pull that electron off. Okay? So you were totally on the right track the whole time. I'm just trying to get to the sort of specific terminology that they're going to ask you to use. Okay. So across a period, as the nuclear charge increases, the attraction increases, and it takes more energy to pull them off. And also because the atomic radius decreases. So that is also playing into it. As the atomic radius is decreasing, we also have our electrons closer to the nucleus, which we know distance matters. So we've got stronger forces pulling on the electrons, and now they're closer, which makes the force stronger. So it's sort of like this circular thing going on here that increases the overall attraction between the nucleus and any one of the valence electrons. Okay. If you look at going down a group, again, it's not always obvious, but you can generally see a trend towards a decrease. So we start with a high ionization energy at the top of a group, and it goes down as we go down the group. Why is that? Kathy? Yeah. So while our effective nuclear charge, it's staying similar within a group, but we're getting further and further away, right? So we have more protons, but we also have more shielding electrons, so that's going to balance things out as far as our effective nuclear charge goes, but we also have an increasing distance. So if you look in that section on your study guide, the valence electrons are further away, and there's increased shielding. Both of those things are going to lead to a weaker force of attraction. It's going to be easier to pull off an electron. Okay. I think we will stop here and leave the exceptions for Thursday. So that we'll also talk about, you may have noticed in looking at this that there's some parts where, all of a sudden we get brighter green here. Why is that? We're going to talk about that on Thursday.